Hello team and hello Professor Tasmin. Um, I think we just wanted to give an update on the project. So here's the prototype. It has the top piece on and all the wiring. And we did add some new wiring, as you can see on the screen. I wanted to go through it just to let you know what's happening and what new pieces, modules we added. So let's start with what's new. This is the MPU 6050. That is a gyroscope and accelerometer. It also is a thermostat, but we're only using the gyroscope features, which I think I said in an earlier meeting that these DC motors don't know the revolutions they made or the direction that they're spinning. They only know if they're on or off, and then the time duration that they ran for. So with the gyroscope, we can calculate the angle to turn more accurately rather than based off of time. So you could put the device on a carpet or on tiles or on wood, and it would turn the same direction either way because it's doing it off of the angle and not off of the time duration it's spinning at. Um, we're also using a keypad for user input to enter the route or the destinations that the user wants to go to. It's outside of our, it is outside of our scope that the user input and user interface. So, but we did want to put in some way that the user can enter in, okay, he wants to go to bakery, meats, produce. That's it. Not all of them. Or they want to go to all of them. Or they just want to go to one. So that's how we're taking the user input. And I just wanted to say we are using every single pin on the Arduino, which is pretty cool. Like I've never had the opportunity to take advantage of all of the Arduino's pins, and the motor shield takes up all of the digital pins of the Arduino. So luckily, there were two pins on the motor shield that could be soldered off, and we could reuse them because they weren't necessary for the motor shield. That's how we connected the ultrasonic sensor. Um, we added the battery, the 8650, because we found that we needed that to drive the four DC motors, which we talked about in the interim report. Now, I wanted to show you the code. Yeah, because I think it's pretty interesting and I'll give you more insight of how it works. So at the beginning, we're just including the libraries for each of the modules. The We are using an Adafruit library and the AF motor because they're an open source, and it's basically they just allow like an easier interface between the AF and not the AF motor, the keypad and the motor shield, because programming it by hand would be a whole different problem. The keypad is these are just the variables for the keypad. We did run into a problem, like I said, that we we're running out of pins. We have no extra pins, and the the keypad takes 5 pins, and we only had 4 available. So we ran into a problem like saying like, oh, okay, how are we gonna connect this keypad? How are we gonna get user input if we can't get this keypad in? So we thought of the issue and we figured out that when the user is using the keypad, the device is never moving. And because the pin A4 is only used for the MPU 6050 sensor, we can repurpose that pin when the user wants to give input to the device. So we use the Arduino's internal clock to switch between like an input and like like the input for the MPU 6050 and the keypad input, which was really smart, to be honest, because we are running out of I/O. We did run out of I/O for the Arduino Uno. Next, just initializing the keypad, and then we declare the timings for checkout to bakery, checkout to produce, checkout to meats, checkout to like all the places. And these are all in milliseconds. They're not in. That's why they're so big. That's why the checkout to bakery time is 3.4 seconds it'll take. So these are all milliseconds. And to find the shortest path between the destinations, we we thought of to use the problem the traveling salesman algorithm, which is a very famous algorithm. It's a Google MP hard problem. It's usually on Google like exams and Google tests and stuff like that. Very famous problem. And it's not that like it's a well-known problem. There are solutions online. The thing is that there is no like solution for the Arduino, because the Arduino, even though it runs the it runs C++ code. Like this is all C++ code. It doesn't have access to the libraries that regular programmers are regular programmers are accustomed to. Like we don't have queues, we don't have stacks, we don't have data structures. Like we have very lightweight data structures, which would make it very intensive for the space problem. So as you can see in the bottom of the output right here, the sketch uses almost 60% of the storage space and 75% of dynamic memory. Like this is the most I've ever taken advantage of on an Arduino. And if we wanted to use, like, say, a queue or a stack or a data structure, like if we wanted to make one ourselves, it would it wouldn't work. It would take over the dynamic memory. So we had to. It was actually like it was a hard problem, because we had to think of a way to find the shortest path, but do it in a very efficient way that wouldn't compromise on our storage space or time, like the duration it takes to actually calculate that. So here, I'll bring up what an actual traveling salesman problem is. This is the traveling salesman problem. There's two ways to solve it. It's naive and dynamic. And basically the traveling salesman problem is you have a salesman, he wants to go to 5 cities, and he can only go to a city once. And you have to find the shortest path between that and all the cities. And it's usually the cost of going to a city is usually the distance between the cities. But for our problem, instead of using the distance between the checkpoints, or the produce to bakery or produce to dairy or something like that, or dairy to produce, whatever, we use the time it took to get to each location. That was our cost matrix. And like I said before, there's two ways of solving it: the naive and the dynamic programming way. The thing is that the naive way is time complexity O to the n factorial. And the space complexity is also O to the n factorial, which is huge, like massive, like very big. We don't want that. Like we wouldn't be able to work with that. So the only option was basically dynamic programming, which is where you use recursion to solve the problem in parallel with each other. So you call the function in itself to solve it in another stream, which is O to the n times n squared, which is that's the big O. That's the time complexity, which you might think that is bigger than O n factorial, but it's not. N factorial is very big. It's a very big number. So let's go back to the code. So I'll go into how we solved the traveling salesman problem in a second, but this is our cost matrix, which is the time between each destination, and the zeros indicate, okay, you're already at that destination. Like C0 and C0, there's no time to get there. It's infinity, it's zero. So there's two ways to solve that. You can either use infinity as a representation, or you can use zero. And because infinity would take up a lot more space than zero, we use zero. And C0, like for the matrix, C0 is the checkout, C1 is the bakery, C2 dairy, C3 is produce, and C4 is meats. These are just some variables for the traveling salesman problem, which I'll go into. And then we have a refactored array, which I'll also go into in a second. But I want to talk about orientation first. So orientation is basically, okay, say I'm coming from checkout to the bakery. I'm going to be traveling south. But what if I come from the meats to the bakery? Then I'm traveling north, or west, and then I'm turning north. So the direction of how you reach that destination matters. So that's why we had to track that. And then these are just the variables for the sensors, the MPU sensor, the ultrasonic sensor, which we talked about in the interim report. As a refresh, the ultrasonic sensor just basically sends out a sound wave, it waits for that pulse to come back, and it calculates the distance based on the time it took the pulse to come back. Okay, now let's get into the meat of the problem, which is the traveling salesman algorithm. The traveling salesman algorithm, basically, it works by doing matrix multiplication. It's very, when you think about the problem, it's not that hard. Like any human could look at like that situation and do it. The problem is doing it quickly and efficiently. That is the problem we face because we're already constrained on space, storage space, and dynamic memory. So to do that, we basically, instead of using stacks and queues, we used an array, which was a lightweight data structure, and we use dynamic programming, which recalls the min cost function to run this recursively in different pipes, basically. And then the least function, which gets called right here, which finds the next checkpoint or potential checkpoint, does the matrix multiplication. Um, I'll tell you how. Now I'll run through how the program would work. So this is the main loop, like the main function. It gets the user input from the user from the buttons at the back, which will look better when design day comes. And then it gets that input and stores it in an array. And then it refactors that, and then it takes that user input to refactor the cost matrix. This matrix, so like I'll give you an example. Like this matrix is for all points in the grocery store. But let's say the customer doesn't want to go to the bakery. This whole matrix would still account for the bakery. That's C1 right here, right? And this row. So how would we get rid of that? Well, the answer is you just make that column and that row 0, which makes it infinity. Um, so to do that, we simply use this function, which is the cost table refactor, which basically takes the user's input and then checks if that is the destination they want to go to. And if it's not true, it sets it to 0. It basically takes that matrix and each column that wasn't highlighted from the user's input, it makes it 0, which is negligible. Like the program won't even check there, which also improves on time complexity and space complexity because we're storing a smaller array, which is really good, really smart to be honest. Um, so after it finds that refactored array with, so say like they didn't want to go to the bakery, it'll cut off that row in that column, and then it uses the min cost function to find the shortest path using the traveling salesman problem, which is this one I was talking about with the recursion. After it finds that shortest path, it stores that into another array called the routing table, and then the routing table is just run through a for loop until the routing table is empty. It checks, okay, I'm currently at the checkout location and I want to go to the bakery. It calls checkout to bakery, and then same thing. Like just whatever location you're at and wherever you want to go, it calls that function. And then all these if else statements are really good because say I'm currently at the checkout and I want to go to the bakery. If this case proves true, all these other cases are ignored. So this also saves on time complexity because we're not checking each and every one. If one is correct, all the other ones are not correct. Like it doesn't matter. But the only problem is that say like all these ones are wrong and then this one finally is correct. This one would go through and then all the other ones would, this would execute and then the ones underneath it would not get checked. So it's basically an ode to the n minus 1 for this function. Ba, ba, ba. Yeah, so basically this If this for loop is what does the traverse, like what chooses the, okay, I'm going to this one now, I'm going to this one now, I'm going to this one now. And let me show you one of the, okay, let's check out bakery. So say I'm at checkout and I want to go to bakery. The traversal time is declared at the top, and then it calls the traversal uh, function, which basically travels straight, and then it counts using the Arduino's internal clock the time the time it takes for while it's moving, and then it does this until the travel time is reached. And then when the travel time is reached, okay, we're here, we stop, and then we go on to the next function. But say like an obstacle is in the way of the cart. If the obstacle is in the way, then a pause timer is incremented because we're not reached the destination yet. We're just blocked by something. So it increments this pause timer until the object is moved, and then it keeps going with the elapsed time, minusing the pause time. So it continues to move, knowing that, okay, I did it. Like we're still we were paused for a while, but now we're moving again. Let's resume. And then after it does the traversal, it stops the move, and then before it does any turn, the ultrasonic sensor here turns left or turns right to check if an obstacle is in the way. Because if it just turns like this, what happens if someone is standing right here? You get hit, right? So it checks first, and then it turns, and then it turns back, which is basically common sense. You look before you cross the street, you look before you turn. We just have to program that. And then it's just simply after it looks left, it turns left, and then it reports back the location. Okay, I'm now at the bakery, and it returns the direction it's facing. And that is basically the program. It is a lot more complex than I thought it was going to be when we originally thought of it, but it is working, and I'll show you a video now of it working. And yeah, I'm really proud with the work that we've done, and all of us are. I think we're ready for our. We're making really good progress for the final presentation. The only thing we have to do is continue error checking and edge case testing, and just cover up maybe the borders of the wiring so it looks more aesthetically pleasing. Okay, thank you.